Oh, uh,
Is it not working?
Yeah,
oh,
I can see you.
Oh yeah, I'm
got
just
it.
trying to zoom in on us.
Yeah, good. How are you guys?
Good.
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 Mhm. It's Friday, so that's
It is
good.
Friday. That's always a good thing. Is it cold down there? Did the cold get to where you are?
Yesterday it was kind of cold, but today it's like 50s.
Hmm.
Yeah, 50s.
It's gonna get a little bit warmer.
Yeah,
Yeah.
but it might sleet.
Yeah, that's gonna be bad.
That might be weird.
Walter is in Boston today.
That's cool. Oh, he's doing the Harvard thing, right?
Yeah. I hope he can get where he wants to be.
Oh yeah.
We've had 100 inches of snow this winter.
Ooh.
Madness.
Yeah,
Winter Wonderland.
I know.
Kinda envious. Maybe just give us 10 inches over here.
Maybe
We'll be good.
like 2 or 3.
You get any snow? Sometime? Occasionally.
This year we didn't. Like, we got, like, a flurry or two, but then, like, nothing sticks, usually.
Yeah.
Usually it's just ice
Uh-huh.
on, like, open and stuff. But other than that, yeah. How about y'all? Y'all usually don't get stuff, right?
No, we're dry and warm. It's bad. There may be some rain coming in March, I hope, because it's the driest winter so far ever. Driest and warmest. Yeah, no good. I mean, it's pleasant, but that's not what we need. Uh, okay. So, welcome. First thing is quiz. And the password is quadrilateral. So you got to know how to spell that.
That's long.
Did you spell it right?
Yeah. I'm done.
You're done. Okay. You submitted.
Mm-hmm.
Logan, you close?
Yeah, I'm on the last one.
On the last one, did we just have to state the theorem that we...
Yes. Yes. That's all. So, Ryan, the next thing is presenting your proof. So maybe get that. So that's the symmetry definitions and proofs, number 7. Or if you did it in a separate document, that's okay too. Oh, no, I'm sorry. That's not the next thing. That's the thing after. The next thing is the transforming graphs.
Okay.
Okay. Okay, Logan?
Yeah.
Okay, so make sure to submit. Okay, now you guys need to go to Adobe Connect. And that's working now. And in order to get it to record, I now know that I need to, yeah, it's on the right screen. I need to make sure it's on the right screen, which it is. Okay. So now I'm in Adobe Connect, and you're in. Good. Okay, so I need to make you presenters. Okay, you're now presenters. Good. Okay, so let's see. Over here. And now. Okay, I'm sharing my screen, but I don't want to. Oh, yeah, I do. Okay. But now you guys are presenters, so in Adobe Connect, you should be able to share your screens.
Yep.
Right? So, Ryan, why don't you start? Share your screen.
With the transforming?
Yeah.
Okay. It's doing the pop-up thing. There we go.
Yeah. All right. Okay. So yeah, let me see what you did with exercise 1. Ryan?
Yes. Oh, exercise 1.
Yeah. It's toward the end. There we go. All right. Okay, there's an answer. Tell me how you did it. Yeah, you need to show a little more work in that.
Yeah. I'm not really sure how to use the procedure that you gave us.
Ah. Okay. So let's look at the example then first.
Okay. That one, right?
Yeah. Yeah, right there. Okay. So it says stretch. Well, okay, you can see what it says, right? We're going to stretch it vertically with a factor of 2. Then we're going to translate 3 units to the right and 2 units down.
Okay.
So the transformation is first we have to stretch. So that's x 2y, right?
Yes.
And then we translate. So that means we add 3 to the current x coordinate. So it's x plus 3. And we subtract 2 from the current y coordinate, which is 2y. So
okay, so
yes.
So we find the transformation equation first, and then we find the inverse from that,
Yes.
and then we find the other equation.
Yes.
Okay.
Yes. So you find the inverse. Now, there are 2 ways to find the inverse. I mean, well, one is to undo the operations in reverse order.
Mm-hmm.
So it's easy for, instead of adding 3, we subtract 3 from the x. For the y, we multiplied by 2, and then we subtracted 3. So to go backwards, subtracted 2. So to go backwards, we have to add the 2 first, because we go in reverse order, and then we divide by 2 to undo the multiplying by 2. That's one way.
Okay.
The other way is the standard switch and solve kind of thing. That is to say, if you want to go backwards on the function y equals, well, it's terrible letters. Let's say x, well, some other letter, m equals 2y minus 2, then you could solve that for y in terms of m, and or switch and solve, that kind of thing. Have you done switch and solve when you did inverse functions? You ever do that?
Where you just switch the variables and then...
Yeah, you switch the variables and then you solve. Yeah, yeah. So if you can do switch and solve to do it too.
Okay.
All right. So there's our inverse transformation, however you want to get it. And then that, not inverse transformation. That's the inverse transformation of xy. And then remember that we pick a point xy on the new graph. So why don't you go back to the picture?
The picture? Okay.
Yeah.
There we go.
So that's what we do. We pick the point xy on the new graph. We don't know its equation. We use the inverse transformation to pull it back to the old graph. We know the equation of the old graph.
Okay.
So we plug in the coordinates of t inverse of xy into that equation. So now if you go back down
to the example.
Yeah. And so the equation, remember, was y equals x squared.
Mm-hmm.
So, but now the y coordinate is y plus 2 over 2, and the x coordinate is x minus 3.
Okay.
So we plug those into y equals x squared.
Okay, great.
And then we solve for y, if you want to.
Okay.
Okay?
Mm-hmm.
So, my request in the future is if you don't understand something, I'm supposed to have office hours and stuff. I'm supposed to be available for you guys. So ask.
Okay.
That's what I'm here for. Because class time is so valuable because there's so little of it. So, if we can, you need a little more explanation, or send an email. If you just if you have a specific question, you can send an email, or you can call me, or you can do whatever. All right. So, Logan, did you also not understand this?
I did it like the same way. Like I knew the equation to find the center with a radius 6 and
you know how to do it, but you didn't know how to use this method.
I didn't do it the right way. Yeah.
Or this way. They're all right, but I want you to practice this way because it generalizes much better than the others do. For example, you can use this method to find the equation of a parabola y equals x squared rotated 30 degrees around the origin.
Okay.
Can't do it the way you know, right?
No.
So, we'll have to find the transformation, and we'll have to find the inverse, and we're going to talk about that and stuff. But the same principle applies. That's the interesting part. Okay, you don't have to fix it now, but and I don't want to spend any more time on that. But if you understand, then what I want to see in the homework where I assigned number 4 is I want to see you do the work for 1 through 4. Okay, this way.
Okay.
Fair enough?
Yes.
Yeah.
Thank you.
Okay. So enough of that. Now let's go to, it doesn't help if you don't, okay, I said it. I don't need to say it again. The point was to practice this method. All right, the next thing was your proofs. Which one of you wants to start? Ryan, are you already doing it? Yeah, you're connected, so why don't you start? So get your proof up.
I think I did it better this time, at least.
Good. Okay.
This is where it began.
Yes. If all squares are congruent, then the quadrant. Okay, so talk us through it.
So I basically just took, because the lemma that you gave in your example problem, the first one was very helpful. Mm-hmm. So I basically just copy paste that one.
Okay, so you used that.
Yeah.
Okay.
And then I used the proof for that because that saved me some time and allowed me to get into the actual proof faster. Okay. And I also took your corollary, and I believe that's all I needed.
Okay.
So I started with the theorem, and I said that given the quadrilateral ABC as the figure right here, I was just trying to prove that it had 2 lines of symmetry, one through opposing opposite vertices, and the other through opposite sides.
Okay.
So I started with square ABCD, okay. And I went with I began with this midpoint because from this I could use reflections to map A to A and C to C and then B to D. And since what was I thinking? 1 sec. Let me go down to my actual.
Okay, so E is the midpoint. I see that.
Mm-hmm. All right. So A maps to A, C goes, and C maps to itself. D is the image of B because reflections or isometries preserve distance, and we know that these are all the sides are equal.
Okay, so, wait, slow down. And Logan, you chime in too if you're not clear on something. All right, so let's look at this. Consider reflection. Since A is on the line of reflection, okay. A is the image of itself. Okay, fair enough. And, I see. And B and D are equidistant from A and C. I see. So that implies that, that's right. The locus of points equidistant from 2 points is the perpendicular bisector, and that is also the reflection line. Right.
Mm-hmm.
Okay.
And that's I think that was theorem 2 when we called them that.
Mm-hmm. Yeah, that's right. Whatever it is, doesn't matter. That's right. Good. Okay, that this shows that diagonal AC is a line of symmetry, and it implies that BD is one as well by the same argument. Yeah.
And so I got those two. I got those two diagonals, and I
Okay.
proved those. So I went on to go and add
Mm-hmm.
another one
Mhm.
that's not a diagonal. So
Mhm.
I'm trying to get. So I'm using E again, and it is a midpoint of F and G.
Okay, wait a second. D is the midpoint. So F is the midpoint of AD, and G is the midpoint of BC.
BC. Yes.
All right. How do you know that the midpoint of FG is E?
I guess I would have to prove that in the. That I need to move that down and then prove that.
Okay.
Right. Okay. Well, that's one flaw. So,
You may not need that, but okay, go ahead.
okay, so here's what I put for, let me try to include the image as well. All right, there we go. So I probably will need to prove that that those are midpoints because I actually use them.
Okay. So let's think about this for a minute. Can we prove that that has to intersect at the midpoint? I think we can. Yeah.
Can't we just say that because a reflection is an isometry that A reflected over this reflection line has to have the same distance from the reflection line as, or D has to have the same distance from the reflection line as A.
Yes.
And the same with B and C. So therefore, F and G are midpoints of their respective.
Yeah, but you have to be careful because you have to be careful because it looks like all these things are true, but you don't know. The only thing you've assumed is that the sides are equal. That's the only thing you've assumed, right?
Mm-hmm.
Okay, so how do you know that FG is perpendicular to AD?
Well, if I do say that E is the midpoint of, wait, no, that wouldn't work either.
I mean, you joined the midpoints. I can see that you joined the midpoints, and
because that's the midpoint of this line, would that would mean that okay, so since E is the midpoint of FG, then I don't know.
It's so easy to assume that things are true because they look so wonderful, right?
Yeah.
So you really have to bear in mind, how do I know this? How do I know this? Keep asking yourself that question. all the time. So,
Could I prove that by reflecting the or FG over AC, the diagonal,
let's see.
and
If you reflect it over the diagonal,
then I would get the horizontal diagonal, or not that horizontal diagonal, the horizontal.
yeah, no, I understand, but you know, you have to show that. I mean, the only thing you would know is that AF prime is equal to AF. You'd know that because reflection preserves distance. You'd also know that reflection preserves angles, and maybe having the two diagonal lines of symmetry could really help you here. So, you know, before, I guess what I'm thinking is, and I may change the homework. I mean, I'm looking at the homework, and I said prove two more theorems, and maybe revising. Yeah, I think I'm going to change that. Revising a theorem is maybe a better idea. Because I think what you could do is really milk what you did in the first part to get a lot of properties of the square.
Okay.
That you kind of know, but you don't, but you haven't proved.
Okay.
And then once you have those properties, then once you have that that if you can show that FG is perpendicular, you're home. The rest is easy because then A has to reflect onto D and B has to reflect onto C, and you're done.
Okay.
So the key thing is to show that's perpendicular, but in order to show that's perpendicular, it would really be nice to have 45-degree angles,
Yeah.
And maybe you can do that using both diagonals. And remember, we do know that the sum of the angles of a triangle is 180. We proved that. And you could prove that the sum of the angles of a quadrilateral is 360 pretty easily.
Okay.
So, yeah. So there's a thought. So I'm going to add revising to the homework. So yeah. So and also I just want to point out that you don't have to repeat the whole, like if you go back a little bit to the lemma.
Yep.
Yeah, you don't have to. You can use the result. In your proof. You don't have to. You don't have to state the lemma in the proof anymore, or the corollary, or whatever. You just refer to them because
Okay.
we've done it. I'll put those in. If I didn't put it in our theorem list, I'll put them in because, as you say, they're useful.
Okay.
But yeah, just state them. Say, we know this. We did it.
Okay.
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 Good. I mean, that was good thinking, good diagram, and you can use everything you've done, but just tighten it up a little bit.
Mm-hmm.
And it's been a long time since you've done these proofs, right? How many years has it been?
4, 3.
Yeah, a while. So that's useful. But that kind of thinking is useful in more abstract, more advanced math too. So it'll get you into that. All right. Logan, why don't you share your screen and show us what you did?
Was this part of the 17th homework? I didn't do this at all.
You didn't do it at all. It was part of the 17th homework, yes. Pretty sure. Yeah. Select another theorem. Yeah, number 3. Select another theorem from the proving that a quadrilateral is specialist, and prove it.
Okay. Well.
Okay. So you don't have anything to share at this point. Is that what you're telling me?
I went into the theorems in TransGeo reference.
Right.
And I couldn't find proving I saw this. I saw the properties of special quadrilaterals.
It's at the end of that, isn't there? There's a whole list.
I tried to make like a GeoGebra file containing like a parallelogram and like y, like with all its components, and I was just gonna explain it. I don't really know. I got confused. I'm sorry.
Okay, but do you see the list in the
Yeah, let me share my screen.
Yeah, share your screen. Good. Yeah, the file, yeah. The reference, there we go. Now go to the end.
You're just supposed to pick one of the.
Wait, no, after the properties. Keep going. Is that all there is?
Yeah.
I sure thought that that there was more. Okay, did I forget to upload the latest version? Possible. Yeah, look in the reference and open that up. Yeah, you don't need to. Just okay. So go to the end of that.
Yeah, it's not there.
Huh. That's my fault. Okay. Because I do have a whole list. Okay, my fault. Sorry. I will put up the correct version with the new things in it. Yeah, no, mine has it, but I guess I forgot to put it up. Okay, so my bad. No wonder you were confused. All right. Yeah, but again, that's something you can shoot me an email and say, you say there's another theorem from the proving that a quadrilateral is specialist, and I don't see a proving that the quadrilateral is specialist. Mr. Douglas, what's going on? And I'll say, uh-oh, and I'll put it up.
Yeah.
Right? And then we would have been ahead of the game a little more. I'm not perfect. Okay. So please communicate more. That would be helpful. Okay. So we're done with that. So let's do. So now I'm going to show you guys some fairly difficult stuff. Do a little better job. So you can stop sharing your screen, and I'm
look at that. At 12 a.m. in the morning. Oh,
Say again?
I said I can't believe I submitted at 12 a.m. in the morning.
Yeah.
Basically today.
Okay, share my screen. So I do this, and then I want this. Yeah, the main display is what I want. Okay. Okay. Now I don't want to get up Word. All right. Can you see something? It says advanced symmetry definitions and proofs. Just that Word document? Yes?
Yes.
Okay.
Mm-hmm.
Okay, that's not the one I want. So the one I want is this. Yeah. All right. So I'm gonna be a little more thorough here and go through this carefully. How much time I do it? 15 minutes. Wow. Okay. I was hoping for more. All right. So, number one was to show that the composite of reflections in three parallel lines, and I'll put these files up also, if it's helpful. I think it will be, is a reflection, and describe the line of reflection. We talked about this, but I did a little more thorough job. So, let me get this up. Yeah. And this, what happened to E? All right. Let me do something for a second. E, yeah, okay. There's E. All right. All right. So this is, the parallel lines are A and B and C. Okay. And we're going to reflect E first in A, then in B, then in C. You with me?
Yeah.
All right.
Yeah.
Now, remember that I said that it's useful to consider a special case first. And the special case is, suppose E is on line A. Suppose E is like that. Okay?
Okay.
Then that's already E prime. It's the same one. It's a fixed point. So we're now reflecting over only two parallel lines, B and C.
Yep.
Right? And we've shown what about the reflection over two parallel lines? It's equivalent to what?
A translation by a vector equivalent to or double the distance between B and C.
Right, and what's the direction?
Oh, perpendicular to A.
Yeah, perpendicular to the lines, right. So with that, that means that the distance between B and C is n.
Okay.
So that's equivalent to, so this distance from E prime to E triple prime is 2n. So that's where the image will be. It's a translation of 2n. But in general, we're doing more than that. In general, this point E will not be on line A. So there'll be an additional reflection. So it'll be a reflection followed by a translation. And we want to make that into a single reflection. Because it's going to be a reflection because it's going to reverse the orientation and then move it. So it's going to be, the orientation's going to be reversed. So it's got to be a reflection in this case. I mean, it looks like a reflection. So we want a reflection that's equivalent to the translation. So we want to get to a point 2n to the right, in this case, perpendicular, 2n to the right via a reflection. So where does the reflection line have to be? It has to be, Logan, where does it have to be?
It has to be at the midpoint between A and C. No, not A and C. E and E triple prime.
Yes, that's right. It has to be in that midpoint, which is a distance n. Half the 2n is n. So we take that distance n between line B and C, and we make that reflection line a distance n perpendicularly from it. So the red line is the reflection line.
Okay.
Okay? So that works clearly for the point E right on here. Great. But wait a minute. What happens if E is not on there? Is that still going to work? Well,
No.
one way to check is just to try GeoGebra, right? So let's try that. So we're going to reflect, that's here. We're going to reflect this point E, over this line. Gee, that seems to work. Right?
Yep.
Are we done?
No.
No. Because what?
We need to move it, or we need to move E to the other side to see if that works.
Yeah, suppose it worked everywhere.
Okay.
Which it does. I'll show you. Let's see. Yeah. Okay. Yeah, it works. Okay, are we done? Logan, are we done?
I'm trying to find something. I think so. Yeah. Well, can you take it past the reflection line? Also, the red line, I mean.
Yeah.
Yeah.
Okay.
That's it. Yeah.
Okay, folks, here's something really important. We're not done because it's not a proof. GeoGebra does not prove things.
Okay.
GeoGebra does not prove things. It shows that they seem to work, but that's not a proof because we don't know why. Right? We don't know why that works. Okay, we did this thing. It worked in the special case. We moved it somewhere else, so it works. But if somebody asks you why does that work, we have no idea. So, and the other thing about a proof is how do we know that this isn't just a little bit off, a tiny bit off, and you can't see it, but looks fine. And there are many examples of things. Well, not enough actually. You're not shown enough. There aren't enough examples where something seems to be true, but turns out that it's not. So for those two reasons, that's really important. GeoGebra never proves anything. It generates good conjectures. It's good for seeing why things, how things work, and generating guesses and letting you think about all these wonderful things. But it's never proves anything. So why does this work? So what I did was, and this is probably, let's see. So I'm not going to save this because I like my original. And I shouldn't have done that. Because it turns out that GeoGebra, I understand now that when you get up a new file, and it doesn't have windows, this window thing doesn't really, I don't know what it's for, but when you get up a new file, it automatically closes the old one. So that was special, and now I want general. Parallel lines general. And so let's see if we can really work through this. Okay, so look at what I did. What I did was, here's the same situation, right? Here's the distance n, and here's the distance n to the big red reflection line, which I called r. Okay? Now, suppose E is not on line A. Suppose E is in fact a distance x away from line A. Okay? Then when we reflect E, then LE prime is going to be x also. So this whole distance here between line A and line B I called M. So this whole distance LO is M, but LE prime is X, so E prime O is M minus X. If that's M minus X, then OE double prime is also M minus X. this whole thing from O to P is N.
Yeah.
So we have to take the quantity M minus X away from N. Right? And we need to distribute the minus sign when we get rid of parentheses. So this is N minus M plus X. Right? And you can check when you add these two together, you get N, which you should get.
Okay.
So E double prime P is N minus M plus X. That means P E double prime is also N minus M plus X.
Yeah.
Okay. Now, look at the distance from E to E triple prime. E to E triple prime is 2x's plus 2 times m minus x, which is 2m minus 2x, plus 2 of these. So that's 2n minus 2m plus 2x. I'm distributing at the same time, right? Now, if you look at all of these, there's a plus 2m and a minus 2m. So the m's go away there. There's a plus 2x and a minus 2x. Those go away. So what's left is the 2n here and the 2x here. So 2n plus 2x. So this whole distance is 2n plus 2x. Doesn't depend on m at all. Doesn't depend on the distance between A and B. Interesting.
Okay.
2n plus 2x. So, but R is the reflection line, and it's in the middle. It's the one we use. So the distance from E to the reflection line is going to be half of that, which is x plus n. But that's perfect because the distance from E to A is x, and the distance from A to the reflection line is n.
Okay.
So a reflection line of x plus n is really going to land E on top of E triple prime, even though E is no longer on line A. Okay? Now, one could say, okay, what if it's on the other side, and what if it's here, and, okay. I mean, that's fair. And so, one technically, I suppose, would have to make other arguments that are similar. You get the idea. That's kind of tedious. I don't think but I think it's important to at least, show that, gee, this works when E is not on line A, at least to the left of it. Okay. All right. So that was the point of that. Now, the second one was concurrent, and since that's similar with angles, but given the fact that we're really short of time, I'm going to go on to something else. I'm going to go on to number 3A, which we talked about a little bit last time. So I'm going to open, which is the special one, B and C parallel. Yeah, it's special in general. So this is going to be at least our special case. So it could be that one, right? B and C parallel special. And what it does is, see, it closes the previous one and opens this one. So this time, this is 3A. B and C are parallel, and A is not parallel. And we're going to reflect E across A, and then reflect E prime across B, and reflect E double prime across C to get E triple prime. All right? So we're going to make our special case first. So our special case is what? Where are we going to put E?
On line A?
Yeah, we're going to put E on line A. Okay, that makes it a little easier. Okay, so
we're trying
E
to prove
is on
that
line A now. And now we're going to reflect E. Close enough, there. We're going to reflect E across B and C. First B, then C.
Okay.
Okay. So that reflection, I'm sorry, that composition of reflection is equivalent to what?
A translation.
Yeah, translation. Logan, keep going. A translation how?
That's 2 times the distance between B and C,
Yeah, in what direction?
perpendicular to both
Okay,
of them.
good. So it's a translation, 2 times the distance, right?
Yeah.
But again, we want to make it there's going to be a reflection over A, right? So there's going to be a reflection involved. So there's going to be a reflection involved somehow. But it may not be a pure reflection. It may be a glide reflection. In fact, that's what it turns out to be, is a glide reflection. So how are we going to do this? We need a glide reflection, and we need yeah.
We need.
So where are we going to draw? Where are we going to make a reflection line? That's, I guess, the point I want to make.
Okay.
Similar to last time. When we had 3 parallel lines, where was the reflection line?
It was x or n minus x or x plus n.
Don't be confused by that last argument. Let me go back to.
So would this just be halfway in between, or halfway the half the distance?
Hold on. Yeah. Okay. Say again.
Half the distance from or between E and E triple prime parallel.
Yes, but how does that relate to N? N is the distance between the lines.
Isn't it just N?
Yeah, we want to go a distance N from here, right?
Okay.
And that's how we're going to locate that line. So we want to go a distance N from there. So let's see how we do that. What angle are we going to go in? Or how are we going to get this perpendicular? What angle is the reflection? See, the problem is that we want to try to make whatever we're doing as independent of E as we can, even of as E prime.
Would it be something to do with alpha?
Yeah, that's right.
Would it be double alpha?
Well, what angle is our reflection line going to make with A?
It's gonna make it's gonna make the angle alpha.
Yeah, it's going to make the same angle. So we want to use that. Okay, well, we're out of time, but that's the way you want to start thinking about this. Okay. Is you want to do that kind of thing. You want to get a reflection line. You want to at least be able to get this point onto here, onto E triple prime before you via some kind of reflection, and then play around with it when it's not on that line, when E is not on this line, and you'll have to, it has to do with it has to do with that angle. You're gonna need that angle. Okay, well, that's all the time I have. I may make a video. I'm gonna try Camtasia, and if I do, I'll post it, and I'll instead of making an announcement on eCollege, which you may not go to, I'll send an email.
Okay.
Okay. A little more. All right, but we're out of time for today.
Thank you.
Yeah, thank you.
So
Have a
we'll
nice
see you
day.
guys. Have a nice weekend.
You too.
You too.
Okay.